The asteroid belt represents one of the most fascinating regions in our solar system, containing a diverse array of celestial bodies whose compositions tell a complex story of our solar system's formation and evolution. This circumstellar disk, located between the orbits of Mars and Jupiter, contains millions of irregularly shaped bodies of varying sizes and compositions that have intrigued astronomers for centuries. The asteroid belt, often referred to as the main asteroid belt or main belt, is a torus-shaped region spanning the space between Mars and Jupiter, approximately 2.2 to 3.2 astronomical units, AU, from the Sun. Despite popular misconceptions, the asteroid belt is predominantly empty space, with the average distance between asteroids being approximately 965,600 kilometers, 600,000 miles. Though this varies among asteroid families and smaller undetected objects might be even closer. The region contains a vast number of solid, irregularly shaped bodies ranging in size from microscopic dust particles to dwarf planets, with the total mass estimated at approximately 2.39 × 10^21 kilo, which represents merely 3% of the Moon's mass. Structurally, the asteroid belt is organized into various groups and families with similar dynamic characteristics, including the Hungaria, Cybele, Hilda, and Trojan groups, as well as numerous families like the Flora family that likely formed from the disruption of larger parent asteroids. The 4-1 orbital resonance with Jupiter, situated at a radius of 2.06 astronomical units, effectively marks the inner boundary of the asteroid belt, as perturbations from Jupiter's gravitational influence send objects in this region into unstable orbits. The compositional diversity of the asteroid belt provides crucial insights into the formation and evolution of our solar system. 3 primary compositional categories dominate the asteroid belt: C-type, carbonaceous; S-type, silicaceous; and M-type, metallic asteroids, with additional hybrid and rarer classifications accounting for the remainder. C-type carbonaceous asteroids constitute the most abundant group, comprising over 75% of known asteroids. These objects are characterized by their extremely dark, coal-black surfaces, with very low albedo and chemical compositions that closely resemble carbonaceous chondrite meteorites found on Earth. Their surface compositions align remarkably well with the primordial composition of the early solar system, minus volatile elements like hydrogen and helium, making them valuable time capsules from the solar system's formation period. S-type silicaceous asteroids form the second most common classification, representing approximately 17% of all known asteroids. These objects are characterized by their relatively brighter appearance compared to C-types and their composition of silicates mixed with metallic nickel-iron compounds. S-type asteroids dominate the inner regions of the asteroid belt, within 2.5 AU of the Sun, and become increasingly rare at greater distances, suggesting significant thermal processing of their materials through melting and reformation. M-type metallic asteroids comprise the third major classification, typically located in the middle region of the asteroid belt with a peak distribution at around 2.7 AU. These objects are relatively bright and primarily composed of nickel-iron metals, with some scientists theorizing they may represent the metallic cores of differentiated progenitor bodies that experienced catastrophic disruption through collisions. A distinct compositional gradient exists across the asteroid belt, with asteroid types distributed in a pattern correlated with increasing distance from the Sun: S-type, C-type, P-type, and finally the spectrally featureless D-types in the outermost regions. This distribution pattern reflects the temperature gradient that existed in the early solar system, with the temperature in the asteroid belt varying from approximately 200 K, 73 degrees C, at 2.2 AU to 165 K, 108 degrees C, at 3.2 AU for dust particles. While C-type carbonaceous asteroids dominate the overall asteroid population, particularly in the outer regions of the belt, they comprise only about 40% of asteroids closer to the Sun, according to the European Space Agency, where S-type asteroids become more prevalent. Several subgroups exist within the primary classifications, including B-type, F-type, and G-type asteroids within the broader C-type category, each with subtle variations in composition and spectral characteristics. V-type vestoid, or basaltic asteroids, represent one of the more intriguing mysteries of compositional distribution, as theories of asteroid formation predict that objects the size of Vesta or larger should form crusts and mantles primarily composed of basaltic rock, which would suggest more than half of all asteroids should be composed of either basalt or olivine. However, observations indicate approximately 99% of the predicted basaltic material is missing from the asteroid belt, with only a few notable exceptions, including the asteroid 1459 Magna and two outer belt asteroids, 7472 Kumakiri and 10537 1991 RY16, which possess distinctive basaltic compositions different from those originating from Vesta. The current compositional diversity of the asteroid belt reflects its complex formation and evolutionary history. The asteroid belt formed from the primordial solar nebula as a group of planetesimals, the smaller precursors of protoplanets. However, gravitational perturbations from Jupiter disrupted the accretion process that would have led to the formation of a planet in this region, imparting excess kinetic energy that shattered colliding planetesimals and incipient protoplanets. During the early history of the solar system, asteroids experienced varying degrees of melting, allowing elements within them to differentiate by mass, with some progenitor bodies potentially undergoing periods of explosive volcanism and forming magma oceans. This melting period was necessarily brief compared to the larger planets due to the relatively small size of these bodies, and had generally concluded approximately 4.5 billion years ago, within the first tens of millions of years of the solar system's formation. The asteroids we observe today are not pristine samples of the primordial solar system, but have undergone considerable evolution, including internal heating, surface melting from impacts, space weathering from radiation, and bombardment by micrometeorites. Computer simulations suggest the original asteroid belt may have contained mass equivalent to Earth's, but primarily due to gravitational perturbations. Most of this material was ejected from the belt within approximately 1 million years of formation, leaving behind less than 0.1% of the original mass. Recent research has revealed extraordinary compositional aspects of certain asteroids that challenge our understanding of planetary science. A handful of asteroids in our solar system, classified as compact ultra-dense objects, QDOS, exhibit densities so extreme that no known element on Earth can fully explain their properties. One such asteroid, 33 Polyhymnia, located in the main asteroid belt between Mars and Jupiter, has puzzled scientists with its unexplained density, as this 34-mile-wide object lacks the mass required to compress minerals into such ultra-dense forms. A study published in September 2023 in the European Physical Journal PLOS proposed that these unusual densities might be explained by the presence of naturally occurring super-heavy elements beyond those listed in the periodic table. These hypothetical elements would exist in the theorized island of stability around atomic number 164, where super-heavy elements might resist rapid radioactive decay and maintain stability for meaningful periods. The existence of water within asteroids represents another significant compositional discovery, with evidence suggesting some asteroids contain water despite being too small to maintain an atmosphere. In 2006, a population of comets was discovered within the asteroid belt beyond the snow line, the distance from the sun where temperatures allow water to freeze, which may have provided a crucial source of water for Earth's oceans. According to some models, outgassing of water during Earth's formative period was insufficient to create the oceans, necessitating an external source, such as cometary bombardment. The compositional diversity of the asteroid belt provides a fascinating window into the formation, evolution, and dynamic processes that have shaped our solar system over its 4.6 billion-year history. From the carbon-rich C-type asteroids that dominate the outer belt, to the silicate-rich S-types of the inner regions, and the metallic M-types between them, these celestial bodies preserve crucial information about conditions in the early solar system and the processes that have transformed them since their formation. Recent discoveries of extraordinarily dense asteroids potentially containing elements beyond our periodic table and water-bearing asteroids that may have contributed to Earth's oceans continue to expand our understanding of these complex objects. As exploration and research continue, the asteroid belt's composition will undoubtedly reveal more secrets about our cosmic neighborhood, and perhaps provide insights into the fundamental questions of how planetary systems form and evolve throughout the universe.